Hey there, chemists. We're going to look at more enolate chemistry in this lesson, but specifically we're looking at esters. As opposed to ketones and aldehydes, it's true that esters can also form enolates. Oh my gosh, that means we can do chemistry with these things too. So all the additions and things that we've learned lately with ketones and aldehydes, we'll see what happens with esters. This is called the Claisen condensation, named after Rainier Claisen, who was the principal developer of this reaction back in the 1800s. He was actually a student of Kekule's, Auguste Kekule, who was the first one to propose his theory of what everyone calls the Kekule structure of benzene, which we now take for granted as looking like that. But before things like NMR and other structure determination techniques, it was not known that that was the exact structure, but that was Kekule's theory, and in his lab is where Claisen worked. Anyway, the Claisen condensation starts with esters, and you get a beta keto ester. Hint, that's a great thing to use to form an enolate and then do some chemistry like we saw before. So we're going to see lots of ways to finally make the things that we've been using in this unit. Let's take a look at how it works. I'm just going to use a generic ester for this example. Remember, an ester has an alkoxide group on one side, and as long as it's got some alpha hydrogens, you can treat that with base. Typically the reaction is done with an alkoxide that matches whatever type of ester it is. So if this is O-methyl, this would be methoxide. If it was O-ethyl, it'd be ethoxide. And you can imagine why, because remember how esters work. Esters can also get attacked at carbonyls, and they can do substitutions. You could do a transesterification, but here OR substituting for OR is degenerate. So instead, we have this acting as a base and forming an enolate. Even though that's an acid-base reaction, and you all know that's very fast, still trying to minimize any possible side reactions. That's why they do this with a analogous OR group. Then, similar but not the same as the aldol reaction, another equivalent of the same ester that's neutral will act as the electrophile. So enolates are nucleophiles, but carbonyls are electrophiles. So one can attack the other. Just like we've seen esters get attacked in the past, can happen here as well. So far, this looks just like aldol chemistry. I'm going to bring this down just a little bit. So we get a new carbon-carbon bond between what used to be the carbonyl ester and the alpha carbon of the other ester. So this looks just like aldol chemistry. And here, if it was aldol chemistry, we would pick up some source of proton and maybe do a condensation. But remember, esters are very different from the other carbonyls we've looked at. When you have an ester, this OR group can get kicked out from this tetrahedral intermediate, and you reform the carbonyl. This is how nucleophilic ACL substitution works. So think back to our carboxylic acid derivatives. And that's what happens instead. We lose this alkoxide, you regenerate it. And you might go, oh wow, that was so fast, we're done. You are not done. There's actually still more to this mechanism. I just kicked out a very strong base, didn't I? And yes, it could reversibly come back in, but there is something much faster that happens instead, and hopefully that's a good giveaway. You'll do an acid-base reaction and take away one of those alpha H's, and specifically those, because as I think you would imagine, it's pretty easy to form that enolate that's flanked by the two carbonyls. Whoops. Where were we? There we are. So you get a fantastic enolate right in between those two carbons. And it's this enolate that's the most stable thing we've got. The Claisen, like so many of the reactions we've learned lately, is highly reversible. But it's this step that's fairly irreversible, and we sit at that enolate. So you'll notice in every Claisen condensation we look at, it's always two steps. It's base followed by acid, kind of like how saponification was 2 steps. And the second step is just protonation of that anion. So you throw in a source of acid, and you protonate your enolate, and that's how you get your actual beta-keto ester. And that's it. So that's the Claisen condensation, and it gives us these dicarbonyls, which are really useful for doing other reactions. We could enolyze them and do substitutions like we saw in the first lesson of this unit. So let's practice this. Let's do a few and see what kinds of products we get from Claisen-type reactions. For each of these, I'm going to draw as little of the mechanism as possible and just try to figure out what the product would look like. I see what looks like an ester, and I see a ketone. Ketones are actually more acidic than esters. Also, this one doesn't even have an alpha hydrogen. So I know I'm going to deprotonate the ketone. That's what the base is going to do. So I'll draw a little negative charge on the alpha carbon, and then that's going to attack my other carbonyl. That's how Claisens work. So I'll just draw an arrow showing me that that's the bond I form, and then I'll try to figure out what the product looks like. I still have my 6-membered ring from the cyclohexanone, and we have a new carbon-carbon bond with this aldehyde group. What happened to this? It got kicked out. We lost that OR- part back here. It will also get protonated, by the way, so you actually generate some alcohol in this as well, but you're probably in a mixture of this thing and its conjugate acid of the alcohol anyway, so we don't even need to draw it. But that's your product. That's what we make from that. Let's try the other one. Here we have a ketone and an ester. This is going to do an intramolecular Claisen. Intramolecular. And we have a question of what kind of ring sizes we can form and where are our enolates. Well, there's the enolate of the ester way out there, of the ketone way out there, which could form a 5-membered ring. There's the enolate of the same ketone but on the other side, that could form a 3-membered ring. That's not very stable. Or the enolate of the ester, which could also just form a 3-membered ring. We're going to go with that 5-membered ring, so make the enolate as far away as possible on the ketone. Plus, ketones are easier to enolize than esters. Good question to think about on your own. So then what happens? We cyclize, we form a bond between that carbon. We lose this ethoxy group. You'll get a 5-membered ring, and maybe it's worth just drawing ugly first, where you keep both carbonyls, but you have a new bond between them. There's the product of that little abbreviated arrow pushing that I have right there. We lost the ethoxy as an ethanol, and it's worth certainly just redrawing that and making it prettier. That's a 5-membered diketone. Okay, there's one more I want you to try. Hit the pause button and see if you can figure out what happens in this sequence of reactions. This is actually not a Claisen condensation. It's going back to some chemistry we learned in the first lesson of this unit, but see if you can figure out what it would look like anyway, and then come back and check. Okay, let's see how you did. So the first step, this is not extra small, but excess, meaning more than enough of just base. We're going to make an enolate. We're going to make an enolate on that carbon. Then we're going to do an SN2. First thing we learned about enolates is they can do SN2s. It looks like I have 2 possible SN2s, so I could form a bond with one and do a substitution. I'm going to draw that as an intermediate, just so I keep track of my carbons. Looks like we're adding 3 new carbons. 1, 2, 3, and then there's another bromide off of that other 3rd carbon. Well, this must be the reason I have excess sodium ethoxide. I have more base, so I'm going to form another enolate on that same very enolizable position and do another SN2. And you're actually going to force this to form a very small ring. This is one of the best tricks that chemists historically used to make small ring sizes. They do a double SN2 on an enolate, and if you check, you're going to get a 1, 2, 3, 4-membered ring. A little square attached to that alpha position. We're not done. That's just the first part. Next, I see what looks like saponification chemistry, which is actually this whole thing combined, and then decarboxylation. So let's write that and remind ourselves what happens. So saponification is the base followed by the acid. That's from the previous unit. That's an ester reaction. What that does is it changes your esters into acids. And then what does that last part about heat do? Well, heating up a dicarbonyl such as this, remember if you have a carboxylic acid beta to any other carbonyl, you get to lose it as a CO2 molecule and it's gone. So we have a gaseous CO2 molecule, and left behind is that cyclobutane with one of the carboxylic acids. So very common starting materials to use to make these substituted carboxylic acids and acid derivatives by doing this little double SN2 trick. And you could imagine what would happen if you had a lengthier chain. You'd get a bigger ring size, wouldn't you? Spiraled together on that alpha carbon. Okay, let's wrap this up with just figuring out how we can get some Claisen starting materials. Here's 3 products. Let's figure out a trick of how to figure out what the starting materials were for a Claisen condensation. Just like the aldol reaction and even the Robinson annulation, Claisens make an alpha-beta bond. What you have to do is you have to find the ester and then count off alpha and beta toward the other carbonyl from that. So I'm going to label this alpha and this beta position alpha and beta relative to the ester. And what we're doing is we're making that alpha-beta bond. And just like in the aldol reaction, that same trick works. The alpha position, you fill in with H's. And the beta position, you make it a carbonyl? Nah, you make it an ester. It already is a carbonyl, but the Claisen comes from 2 esters. So we can redraw all the carbons. The piece on the right, I'm going to draw exactly the same. Well, I'm going to abbreviate O-ethyl as O-E-T. And then the piece on the left, I'm also going to draw exactly the same. But it's not that aldehyde. I need to fill this in and make it an ester. So what ester should we use? Let's use the same ester that we have for the other one, an ethyl ester. And once I do that, take a look at those 2 molecules. They are the same. This is a self-Claisen. And that's a nice way of doing a Claisen, because then you don't have to worry about which one is the enolate and which one is the electrophile, because that could be true for either one of them. Let's try the other 2. I'm going to do the same thing. First, find the ester, there it is, and then go alpha and beta to that ester. That's the bond we make in the Claisen condensation. And then I'll redraw all the carbons. This time I'll actually start with the benzene ring on the left. There's that Kekulé benzene structure. The beta carbon, we have to make it an ester. I'll make it a methyl ester, because the other one I see is also a methyl ester, CO2Me, just snaking it down a little bit. 2 carbons and then a methyl ester, 2 carbons and then a methyl ester. So we have a nice intramolecular Claisen. And the last one, same thing. Find the ester, go alpha and beta to it. That's the bond you make. If we draw our starting materials, the piece on the right comes from this methyl propanoate, and the piece on the left would come from a benzoate. And I'll make it methyl benzoate, just to make it the same type of ester. At the bottom, just before we hit stop, there's a note about the Claisen condensation. You will only favor the products, because this is reversible, if there is at least 1 remaining alpha hydrogen on that beta dicarbonyl product. So all of these are possible Claisen products because there is 1 lone H still left behind. And the reason for that is because you have to form that enolate prior to the acidic step. If you can't get to this last enolate, these things actually open back up and go to a retro Claisen just starting ester. So you'll see that we can only get a Claisen product if you have that remaining alpha hydrogen to form the enolate. So only esters with at least 2 will actually form a Claisen condensation product, because one of those alpha hydrogens has to become the new bond with the other carbonyl, and then the other one will become the enolate in the end. So you're never going to see a Claisen on a molecule that looks like this. Can't Claisen. Because there's only one alpha hydrogen to begin with, and we need at least two in order for this to work. Okay, so that's how the Claisen condensation works.